This will be a video I'm going to go through the common nomenclature for end-of-charge detection for nickel metal hydride cells. In this first picture, we see in purple an area which is the initial upswing in terminal voltage on a nickel metal hydride cell as we begin to supply a constant current charge. At the very top of that, we see that the upswing in voltage levels off as we begin to reach a point where the internal chemistry inside the cell is beginning to catch up with or keep pace with the continuous influx of current. Here in the second picture, we see outlined in purple the area of the bulk charging that occurs during constant current. The voltage stays much more level. The chemical reactions inside the cell that are absorbing or converting that electrical energy to chemically stored energy are at this point keeping pace with the rate at which the current is supplying electrical power to the cell. Here in this picture we see another area outlined in purple where the voltage of the cell is beginning to upslope again despite constant current. The reason for this change in voltage is the chemical reaction inside the cell is beginning to change. Molecule by molecule, they're beginning to get filled or reaching that higher energy state of being fully charged. It doesn't happen all at once, it's little by little. And we also notice that this actually happens before any of the end-of-charge detection mechanisms have identified yet. In this picture, outlined in purple, we see the peak voltage detect indicated. This is the point at which some chargers may notice that the battery is at or near its end of charge. They may either cut back on their current or may terminate their current depending upon the design of the charger. But in any case, we can see at that point that is where we would see it in the voltage graph. In this picture, outlined in purple, we see the negative delta V, or the negative change in the voltage slope. The voltage actually goes down a little despite the constant current that we're still supplying. And that's because the chemical reaction inside the cell is continuing to change as we're changing over from the charging method on the other side of the peak voltage detect to on the back side of it where the battery has already chemically stored everything it can, and there's a different type of chemical reaction going on. In this picture outlined in purple, we see again the voltage of the cell leveling off to a more steady state condition despite constant current. We are now in the tail end, and all of the chemical reactions have converted over past the actual storage of chemical energy, and nothing is being stored anymore. We're pumping electrical energy in, and it's all being converted to other things. None of it's being stored inside the chemical cell anymore. Here we see outlined in purple the beginning of the temperature at the same time of the voltage, which we already went through. The temperature, we can see, does a similar thing where it begins to ramp up from its initial state as some of the energy supplied to the cell, since nothing's 100% efficient, some of it is being converted to heat in the process. That heat slightly warms up the cell, and we can see where it slopes up as it reaches a equilibrium state where it's generating as much as the ambient environment is pulling it away depending on the surface area of the cell. Here outlined in purple we see another steady state condition, this one reflecting with temperature. At this point the influx of electrical current in the cell and the less than 100% efficient chemical conversion into chemical energy is releasing heat energy, the byproduct. That amount of heat energy that's being generated in that chemical reaction, charge-dominated system, is being stabilized and is in equilibrium with the ambient temperature loss based on the temperature of the air and the surface area of the cell in question. Here we have outlined in purple another change in the slope of the temperature. We see it beginning to rise again. This is also an indication of a change in the type of chemical reaction happening inside the cell, as more of the electrical energy being supplied is beginning to get converted into heat. The different chemical reaction that is beginning to dominate is converting a greater percentage of the input energy into heat energy, and less of that input electrical energy is getting converted into chemically stored energy in the cell. Here, outlined in purple, we have a circled area for the change in temperature over change in time. This is a method that some use, that if the temperature of the cell is changing faster than a certain rate, given a change in time, some chargers will use this as an end of charge detection method. We can see, however, that this is already significantly into the point at which the chemical reactions that are inside the cell are becoming much more dominated by electrical energy to heat chemical reactions, and no longer being stored as chemical energy reactions. Here we see outlined in purple the change in temperature. This is similar to the previous one. The difference is that some chargers use an absolute change in temperature method. Instead of referencing it to time, they have a temperature of the initial condition that the cell was put in at, or a temperature of the ambient air temperature in the area, and they compare that to the cell itself. And if the difference in temperature between that initial condition and the cell itself exceeds a certain point, some chargers will use this as a end of charge detection, which, as we can see, is even after the change in temperature over change in time method. But it is another method that is used. At this picture, outlined in purple, we see the temperature cutoff. The temperature cutoff is where the chemical reactions in the cell that are producing heat have completely dominated, and they're producing heat at a steady rate dependent upon our continuous constant current being applied as charging. But now all of it's being converted to heat. Not 100% efficient, but the vast majority is, and it has now reached equilibrium with the amount of heat being generated and the amount of heat being lost to the ambient temperature in the environment. Some chargers will use this as another method of charge termination. In this picture, outlined in purple, we see that there is a PTC area. There's a positive temperature coefficient. This is an area in which some cells and some battery management systems are designed as a fail-safe point, where if this temperature is reached for whatever reason and other end-of-charge detection methods have not been detected yet, this upper end temperature that is kind of getting outside the recommended operating range of the cell is getting reached. There is a positive temperature coefficient that triggers a shutdown of the charging at that point as a fail-safe. Here we see two purple lines. The one on the left is roughly indicating where the voltage is just beginning its upswing as an indicator of some of the chemical reactions inside the cell are beginning to shift over out of the charge mechanism side, and they're leaving that more steady state where they were previously during the bulk charging. And the other purple line on the right of that is where we see the same kind of upswing beginning to happen with temperature. There is a lag between the two, and which one happens that the charger detects, depending on what sensor and what logic it's using, can give you different results for how much overcharging is applied to a cell. I did want to mention that, as we've seen, practically all of the charging methods used for nickel metal hydride are trying to detect things that, or indications of the change in the chemical reaction inside the cell, detecting it after that change begins to become a dominant force, a dominant significant percentage of the chemical reactions inside the cell. By detecting this after the fact, it means that the vast majority of chargers, even smart chargers, actually end up overcharging a nickel metal hydride cell pretty much every single time they charge it. One of the reasons where nickel metal hydride batteries are able to do this hundreds of times despite this overcharging is because the chemistry itself is relatively durable and tolerant to abuse. Although it does get more complicated if we want to try to avoid that end, because we would have to terminate the discharge before detecting those things, before having those outward after the fact indicators. That becomes tricky because we would almost have to have prior knowledge of the storage capacity of the cell. So we're not doing the equivalent of trying to pour a gallon of water into a shot glass. We don't want to overflow it. We don't want to cook it. We don't want to overcharge it and shorten the life of it. And we don't want to waste energy. We want to put in as much as it'll hold and stop. Doing more than that is just throwing energy away and is wasteful, even though it might be easier that way as far as designing a charger. But there you go. An idea that I'm playing with, it might be a long time before I actually start building some prototypes to test it, is to a charge mechanism that's more similar to the way that we charge the more delicate, less tolerant lithium cell family, where you reach a certain voltage and then you keep a steady voltage once that's reached and allow the current to taper off. The reason why I think that might be attractive as a means of efficiently charging even nickel metal hydride cells is because the voltage is a sum of the chemical potential differences between the anode cathode, the chemistry inside the cell. And by having an upper end stop, slowing the current rate would slow the rate at which we're doing it as we approach the end of that charge, just like we see in the lithium family of battery charging. While that idea seems to have merit, I don't want to suggest that it's already been tested or proven. I like the theory perhaps on the surface, but I would want to test it and quantify if it actually is going to be more effective, more efficient. Will the battery take as many cycles that way? What kind of time loss are we looking at? How that's going to work in practical application, and that hasn't been done yet that I am aware of. I haven't read any work yet on people doing that yet either, but that's at least an idea I am playing with.